Welcome to my channel. In this video, I am going to discuss steepest gradient descent algorithm. In steepest gradient descent algorithm, for n-dimensional problem, first we will consider one cost function j, which is function of these n variables w1 to wn. So this is one cost function. Basically, it's a convex function, and our objective is to minimize this cost function and to find the solution for this cost function where the function is minimized. Okay, this kind of optimization technique we have already discussed in my previous lectures, so I'll request all of you to go through those lectures, okay, if you have not gone through this one. Especially this gradient descent algorithm, okay, the link of this gradient descent algorithm will be given above, so you can go through this one if you have not gone through. Now here we'll discuss gradient descent algorithm very briefly. So in gradient descent algorithm, you will see that it is one iterative algorithm. In every iteration, we want to adjust our weight vector. So wk we'll call weight vector. So that is w1k, w2k up to wnk. All the weights are collected here. So that will give you one row, one column vector. Here I'll consider one column vector. So this is wk. So this wk is now updated by this factor minus times mu times gradient of this cost function at that point wk. Okay, so you see this wk is a vector. This is one current weight vector or position vectors, and this is one gradient vector, okay, at wk. So if you combine these two with one mu constant value, then we will get a new update wk plus 1. So this is the simple gradient descent algorithm. Okay, here mu is called step size or learning rate. Okay, so depending on mu, you will get different kind of gradient descent algorithms. So in this lecture, we'll explore this step size in more detail. So what is the effect of this step size? Okay, so in short, we can say if mu is small, for small step size, we can find slow convergence because this update is little. If mu is set low, obviously this magnitude will become low, so little will be added with previous one, so you will get there's a little modification over this previous weight vector wk. Thus the convergence rate is slow. Okay, and if it is used for online applications, then you will see that you will get better steady state. Means when it will reach to this optimum level or global optima, then it will remain there, okay, close to this optimum level. Okay, it won't fluctuate about this point very much. Okay, that means it is having better steady state. Remember, this better steady state is only for the online applications where we'll use stochastic gradient descent. So I'll make another video in detail on stochastic gradient descent algorithm. Okay, there you will see this will play a big role, the steady state one. Okay, and other one, when step size is made large, you can expect that convergence rate will be faster, but we can find poor steady state for online application, right? But here we are concerned about the small step size and large step size, especially for slow convergence or faster convergence. But here it shows that large step size will imply faster, but it is not perfectly true, because if you provide very large step size, you may not get faster convergence. Okay, if it is too large, then the algorithm can diverge. Okay, it's unbounded. It cannot converge to this optimum level. Okay, so we have to make sure that this large step size value should not go beyond a certain level. It should be within one bound. Okay, so that bound is region of convergence that is required, right? So how to set this step size value perfectly so that you will get fastest convergence? So we are concerned about these things here. So what you will do, instead of this one constant step size, now we are going to use one variable step size mu sub k. Okay, we want to set in every iteration one step size so that in that iteration we'll find the best results. Means we'll obtain the optimum step size here to get fastest convergence rate. Okay, so that is the objective here. So if you can solve these things, if you can find the mu k in such a way, and if you replace that mu k here, then that algorithm will be called as steepest gradient descent algorithm. So steepest gradient descent algorithm is the best convergence rate that is produced from gradient descent algorithm. Okay, we need to provide that kind of step size in every iteration. Okay, so that is one basic difference between standard gradient descent algorithm and steepest gradient descent algorithm. In standard gradient descent algorithm, we will work with constant step size. Generally, we will consider small value so that it won't go out of bound, no, say it won't diverge. But if you want fastest convergence, then in every iteration we need to modify the step size. We need to use proper step size, the optimum value for this mu k. Then the algorithm will be called the steepest gradient descent algorithm. I hope it is clear. Okay. Now I'll give you one example. Suppose this point is the initial point. This one is W10 and this is your W20, right? So this is the initial point. Now from this point we'll move, and I have drawn here all the contours. So I think you understand about contours. I have discussed about the contours in detail in first or second video lectures of this gradient descent algorithm. So you can go through that one. Okay. So your optimum point could be here at this point, and this contour indicates that it is having higher error, higher cost, and this one is again higher cost. Like that, the cost is more for this contours, and on the contour, in one contour, everywhere cost value is same. Okay, along this contour, this point, every point, the cost value is same. But if you compare these two contours, this contour is having a higher cost and this contour will be having lower cost. This is again for the lower cost, and here you will have the minimum cost. So that there we want to reach from this point. So we'll start from this point. We want to go to this point, the optimal point. Okay, so how to go? So we'll use gradient descent algorithm. So one descent direction we need to get, then only we can move it. We can move. So what we'll do? First we'll consider one tangent at this point. Then we'll consider one normal to this tangent, and that is exactly the gradient direction. So gradient direction is one direction which will indicate that in this direction the function is increasing with maximum rate. Okay, that is your gradient. So gradient of this cost function will give you one direction in which the function is increasing with maximum rate, and the magnitude of the gradient direction is also given. Okay, we can find out. So if this is the direction at which the function is increasing rapidly, so one expectation is that if we can move in opposite direction of this gradient, then we can reduce the cost functions. So that is the idea of gradient descent algorithm. So we'll move in opposite of, exactly opposite of this gradient descent direction, these directions. But question is how long we'll move. We can move up to this point along this line. We can move up to this point. We can move up to this point. We can move up to this point or this point or this point anyway. Okay. So you can see that if we can move up to this point, this is the point. Then I've said that this is one contour, outer contour. So if this is the corresponding point or final point along this line, then error is not exactly reduced. It will remain same at j equal to 50, suppose. And if you go here, then obviously cost will increase, it will not decrease. So this is one direction. Okay, in this direction, if we move, we can reduce it, but there is no guarantee that in every position you will get less error. So you see, if we can end up to this point, then cost will increase further. So it is not permissible. Okay, we cannot accept this point. But if we come up to this point, you see, along this line, then this cost function is, this contour value is 40. So at this point, your cost value is reduced to 40. Okay. Similarly, if we come to this point, the cost value will be 30. This one. Again, if I move here, again it will become 40. Okay. So from this figure, it shows that this point could be the best one, right? Because it will touch to this contour only. Okay, and other contours, they are going to cut it, this one. Okay, higher contours, they will cut this line, meaning is that you will get higher cost value. And this lower one, so you cannot achieve these things through this line because it will not touch, it will not cut this one. Okay, so I want to find one contour which will touch to this line, and there only we want to stop. Okay, so that is the optimal point here in that iterations. So this is the point. And again, from this point, we'll go through the negative of the gradient. So negative of the gradient is 1 because gradient is this side. Negative of the gradient is this side. So how long will move? Again, this line will touch to another contour. This point, we can stop here. Okay. So this is the point. So from here again, we'll move along the opposite of gradient like this. So again, we have to go up to certain point where it will touch to one contour. So probably it could be here. So though it is not shown here, so I can expect that the point could be here, like this. Okay. So you see, we have got certain points, the steps. So we need to take certain step to come from this point to this point. So you need to adjust the step size so that the point from this point will move to only this point. Exactly. Again, from this point along this gradient, negative of gradient, we need to move up to exactly this point. Then we will get the best results. Then from here, we need to move this one. Okay. So you see. So this is the first step. This is the second step. Third step. And similarly, you will get more steps to reach your optimal point. Right. So this is your steepest gradient descent directions, and after this is the path it will follow. Right. Now, how to get this optimal step size? That is the concern. So what we will do? So this is the update equation for the steepest descent gradient descent algorithm. So mu k we need to find out such that the error is reduced. Okay. So first we will consider the cost function at kth iteration. So at kth iteration, cost could be j of wk, right? And k plus 1th iteration, the cost could be j of wk plus 1. Now we can replace wk plus 1 by wk minus mu k times gradient at wk. So this is 1. So our objective is to find the value for mu k so that at that iteration k plus 1 iterations this value is minimized. So again, one minimization problem, but it is with respect to only mu k, a single variable mu k. So we need to solve these things. We need to find one single variable mu k to minimize this cost function w j of wk plus 1. So we can formulate in this way. Mu k is exactly the solution for these things, minimization problem of this one, that j of wk minus mu times gradient of wk, jwk, okay, and that is argument minimum for which this function is minimized for this mu, that solution will be calling as mu k. So you see this function, this cost is a function of single variable mu that we are concerned about. Okay, we don't consider any other things because wk is known to us. Okay, wk we have obtained in our previous iteration, kth iteration. Okay, this is known, just only mu is unknown. So you want to find this value, mu value, so that this cost is minimized. Okay, so this is standard approach. So how to do? So I'll take derivative of this cost with respect to mu, and then I'll put it 0. I need to solve it. The solution will give you mu k. Okay, so this, after taking derivative, you will get one equation, and that equation will contain a single variable mu. Okay, it's function of mu only, and because others are all known, wk is known, right? So we are expecting that these functions, this function, this is equal to 0, will have one minima. Okay, so it may look like this. So if I plot this cost j of wk minus mu times gradient of wk, so it may look like this. It can have one global minima, and that value is mu k. At mu k, you are having the minimum value. That is the solutions. So we need to find this mu k value, and then that will be replaced here, and we will get wk plus 1 equals to mu k wk minus mu k times gradient at wk, right? And this problem is exactly called exact line search problem, because along the line, okay, this gradient descent, negative gradient descent line, you need to find out one single variable mu so that the function value is minimized. Okay, so this technique is exact line search, so we can use this method to solve these things, but this is really difficult task. Okay, so now I'll discuss a little bit more detail. So derivative of this cost, so you know that j of wk plus 1, that I need to take derivative with respect to mu, and that I will put it 0, and we'll solve it. Okay, now this derivative, what you can write? Can I write in this way, that as this is, suppose with respect to wk plus 1, first we can take derivative of this j with respect to wk plus 1, right? And then we can multiply with d mu of wk plus 1. That's all that we can do, right? So I can consider this is one variable wk plus 1. So what is this? So this is nothing but gradient at wk plus 1. Okay, and what is this one? So now I need to take derivative. So this is not partial derivative, simple derivative, because wk plus 1 is simply wk minus mu times of gradient descent. So this is a simple function. Okay, so this is constant independent of mu, so this value is 0. This is minus sign, this derivative is 1, and this is a constant So this is gradient of wk. So this derivative is nothing but minus gradient of j at wk, right? So what you will get? So from here you can see that this is your gradient at wk plus 1, that we write is gk plus 1, and this one is negative of gradient at k, that so negative gradient that only gk, so you should put minus sign here. Okay, so I am considering this gradient of j at wk is only gk, right? Don't be confused. So negative side is something else, so this is replaced by only gk. So what is happening? This derivative now we can write minus gk plus 1 times gk, and this times this is basically a dot product because these are two vectors, and after operation of this vector you will get one scalar quantity, so this is a dot product. Okay, and this dot product we can write in this form minus g transpose k plus 1 gk, or we can write g transpose k followed by gk plus 1, anything. So a transpose b or b transpose a is same thing, right? So this is your derivative of this cost. Now for optimization I need to put it 0. So what is happening? So g transpose k plus 1 and gk, this product should be equal to 0. So what is the meaning of this? These two vectors, their dot product is 0. It implies that they are perpendicular to each other. They are orthogonal to each other. Okay. So gk plus 1 is perpendicular to gk. So whatever direction you got at kth iteration, the negative of gradient, now at k plus 1 iteration, that negative of gradient direction should be perpendicular to the previous negative of gradient directions. Okay, that is one condition required we will get for optimum reductions. Okay, for steepest descent gradient descent algorithm. So this is one condition, right? So you see in the previous example, so this is your negative gradient descent in the first step, this is the second step, and this should be 90° orthogonal. Okay, 90°. Again, next step is this one. This is 90°. This is again 90°. So every successive directions will have 90 degrees. Okay, so in it is two-dimensional, then obviously these lines and alternate lines are parallels. That is true. But in the higher dimension it could be different. But the directions should be perpendicular in every successive iterations, right? Now I'll consider one simple case that is called quadratic cost functions of this form. J of w I'll consider in this way, half w transpose r w minus b transpose w plus c. Here R is a symmetrical positive definite matrix, right? So what is the gradient at kth iteration? So if you take gradient, so you will find that this derivative is 2 times rw. So 2 and 2 is cancel out, so you'll get only rwk. So at kth iterations, it is w is replaced by wk, and its derivative is simply w. Sorry, with respect to w, I am taking derivative, so it will be only b. So it's minus b, and this is the independent of w, so its derivative is 0. So this is your gradient term, rwk minus b. So what is the update? Update is simply wk plus 1 equals to wk minus mu k gk. So mu k we need to find out. Okay, so this update should be for steepest gradient descent algorithm. Okay, we need to find this optimal mu k for this quadratic cost functions, right? This is the objective right now. Okay, so this is the formulation. right? So what you can write? Gk plus 1. So if gk is these things are wk minus b, so I can replace k by k plus 1. So here it will become r times wk plus 1 minus b. That's simple. This is your gk plus 1. So what is the condition? We have obtained that gk plus 1 should be perpendicular to gk. So I can write g transpose k times gk plus 1 should be 0. Okay, so that will be using. So now I'll modify this thing. I replace this wk plus 1 by these things. This wk minus mu k into gk. Now we'll simplify it a little bit. We'll multiply r with both. We'll distribute these things and then we'll rearrange. So r wk here and this minus b I will take here, and this is r times mu times gk is here. Okay, mu times r times gk. Remember, r is matrix, so mu is a scalar quantity I can take outside, but don't consider gk first. Okay, this r followed by gk only. Right. Now what is this? R wk minus b. This one. This is basically gk. So you can replace that thing as gk. So this is your gk. This one. And this is your mu k r into gk. Right? That is your gk plus 1. These things. Now for the steepest gradient descent algorithm, we have got this condition that g transpose k times gk plus 1 should be equal to 0. Now replace gk plus 1 here. So if I replace g transpose k and this is replacement gk minus mu k r gk, that is equals to 0. Now if I distribute this thing, so g transpose k and gk minus mu k outside, g transpose k r gk, that should be 0, right? So we can solve for mu k from here. So mu k would be this upon this. So g transpose k gk upon g transpose k r times gk. So this is the optimal step size. So if we replace this mu k in original update equations, this one will get steepest gradient descent algorithm. So exact update for the steepest gradient descent algorithm is this one. Wk plus 1 should be equals to wk minus g transpose k gk upon g transpose k r times gk times gk. So basically this is the step size mu k. Okay, this is your steepest gradient descent algorithm for convex quadratic convex functions, right? In upcoming videos I'll consider one example and I'll show you all the steps clearly, how to get the every iterations, and also I'll consider one corresponding MATLAB simulation to show you how it is approaching to these optimal points. Okay, so please keep watching, and if you have not subscribed my channel, you may subscribe it. If you wish to get similar kind of videos in futures, you may like this video. You may share this one to your friends or your known persons who may like this one. So thanks for watching.